So today we're going to do lesson 32, which is going to be all about batteries. We're going to do some calculations and talk about battery components, some kind of conceptual information that you need to make sure you know. And we're getting to the end of the chapter 17 about electrochemistry. So, thermodynamics and electrochemistry. Okay, so we're going to relate delta H to our E cell knot values. In the previous lesson, which would have been lesson 30, we discussed the spontaneity of galvanic cells. So when E cell is greater than 0, we said this was spontaneous, and that is going to depend on who the cathode and the anode are identified to be, because we determine E cell based on the identity. So in the lab you saw that if I switch the black and the red leads to like zinc and copper, the value may be negative. But if I switch them and put red on copper and black on zinc, then it was a positive value, same magnitude, just positive instead of negative, but same number. So we can relate this to delta G naught through the following equation, which is derived in your textbook if you want to know. But you don't have to know how it's derived. You just need to know the formula itself, which is that delta G naught is equal to the negative of N times F times E cell naught. Okay, so N is going to be equal, not moles in this case, but number of electrons being transferred. 1, 2, 3, 100. F is called Faraday's constant, and this value is 96,485 joules per volt times mole. Okay. E cell naught is going to be the standard potential for the cell, and just like we said up there, it's going to be the standard reduction potential of the cathode minus the standard reduction potential of the anode. And so if we look at units, volts, moles of electrons, okay, which will leave us with a delta G naught unit of joules. Okay. All right, so let's calculate the delta G naught for the lead silver cell that we see here. Now the first thing we have to do is we have to remember we're solving for this. We need to determine number of electrons being transferred. We know Faraday's constant, and we need to calculate E cell naught of the cell we're given. The problem is I'm not directly told who is the anode and who is the cathode. However, I do have the standard reduction potentials, which will tell me who's likely to be oxidized and who's likely to be reduced. Okay, so in this case, the more positive value, if you remember back to our discussion before, it's likely to be what's reduced, making it the cathode, what's on the right, whereas the more negative value is likely to be what's oxidized, and that's the anode. So in our galvanic cell image, it was the left side cell, whereas the cathode is the right side cell. Okay, so I have the values that I need because I've assigned them, and we are going to calculate E cell naught off here to the side. Okay, so here is my E cell naught value that I need. I know what Faraday's constant is. Okay, so what I need is N. Now, you might be tempted at this point to add the electrons to say there's 3, right? There's 1 in the silver half cell reaction and there's 2 in the lead, but it's not total. It's going to be the net. So how many are transferred from one to the other? And in order to know that, we need to think about how these two equations would add together. So we know that if silver is losing 1 electron and lead is or if silver is gaining 1 electron because it's reduced and lead is giving up 2 electrons, well, those 2 electrons have to go somewhere. We're not just gaining 1 electron in the silver and then the second electron is floating out in space. If 2 electrons are lost by the lead, then 2 electrons are gained by the silver. Okay, and so if you remember about adding the equations together, we would say at this point, to get the electrons to cancel out, we would multiply the entire half cell equation by 2 in order to get them to cancel out. And then this would leave us with the following, where the 2 electrons are going to cancel out, and that's what my N value is. It's the 2 electrons that are lost from lead that are gained by the silver. And then this would be my net ionic equation. Okay? But there's no electrons in the equation you see there in pink because they cancel out, because they're exchanged. They're not necessarily reacted or produced, they're just exchanged, and so they don't show up in that overall equation. So now I have all the values I need. And so now I'm going to calculate delta G naught. You should make a prediction right here. Is delta G going to be positive or negative or equal to 0? So think about what the sign on delta G would be in a spontaneous reaction, because this suggests spontaneous in the forward direction. So if we're saying it's spontaneous in the forward direction, take 5 seconds and make a prediction, and then we'll see if it's right. Maybe write your prediction off to the side. So now I'm going to start plugging everything in. You do need to know Faraday's constant. Okay? It's not always given on the test, and with this online version of the test coming out, I'm not 100% sure what I'm going to be receiving as far as a table, so you do need to know Faraday's constant. You'll see it in physics anyway, which most of you, if you haven't taken physics, you are going to take physics, and so it's something you will use in physics. So now I'm going to multiply 2 times 96,485 times 0.93, and I get negative 179,462 joules, which I can convert to kilojoules because that is a big number. And so this also agrees, and hopefully you made the prediction correctly, that delta G would have been negative because that's when the reaction is spontaneous in the forward direction. So the two should support each other, the positive E cell naught value and the negative delta G value. Okay? All right, so then this says to derive the relationship between the equilibrium constant, which is K, and E cell naught. So to do that, and on your, I made a note right here that page 924, there is a useful tool. Now the only thing is that this book that I got that page number from was the first edition, and now there's a second edition out, so I'm not 100% sure if it's exactly on the same page, but what it is there is a triangle, and it relates K, delta G, and E cell naught. Okay, so that's the useful tool that I'm getting you, or I'm hoping that you'll go look at if you are unsure. So I'm going to take the equation from a few chapters back, a few lessons back, and the equation we introduced today. Delta G naught, because they're equal to the stuff on the right-hand side, the things on the right-hand side are also equal to each other. It's just basic algebra. The negatives are going to cancel out, and now I'm going to rearrange it for the E cell naught. So I'm going to divide this to both sides. That's going to cancel these out, leaving me, and I'm going to flip it around. Okay. And so I took out the RT and the NF, and I made that into its own standalone thing, and then ln of K. Okay. Now the thing is, all of these are constants except for N. So R, T, and F, remember when we have the naught value here, that means temperature is set at 25 degrees Celsius, which is 298 Kelvin. Faraday's constant is a constant. Ideal gas constant is a constant. So this reduces down to the following. Okay, to where n is the only thing that's not a constant. Now, there is another equation, okay, and they look very similar, except for instead of the natural log, it's log, okay? So if you see this version, it's not that it's incorrect. The only difference between these two versions of the equation is one is natural log and one is log, okay? And then because there's a difference in that, it means that we have to take into different accounts the numerator, okay? So pick one, know one, and use it, okay? So now we're going to calculate the equilibrium constant using the information from cell 1. So in this case, I have, I'm going to use the log one. I don't know why, but when I was in undergrad, this was the form of the equation we used. And the log function on my calculator is on the actual keypad, whereas the natural log is not. I have to go into a catalog and look for it. And so I guess for that reason, I have always used the log version of this calculation. But you should get the same answer. So I'm going to plug in my 2 electrons. My K is what I don't know. So make a prediction. Should K, let me get rid of my table. Should K be equal to 1, less than 1, greater than 1? Okay. And now I'm going to have to rearrange. So I'm going to take the 0.092 and divide it by 2. Which, the only reason I'm showing this math out is because I want to make sure you guys are solving for it correctly. So I'm going to divide those two first. Now I'm going to divide out onto both sides, leaving me with the log of K is equal to 31.4199. There's lots of significant digits. And now to get rid of that, okay, I'm going to raise that to the power of 10. And you're going to get a very big number because it's a very big exponent. And K is roughly 2.62 times 10 to the 31st, which means products are heavily favored over reactants, which suggests that it's spontaneous in the forward direction, which agrees with everything else we have seen up to this point and agrees with the information in the table. Okay? All right. So I'm going to go ahead and stop it here, and then we're going to pick up on this in a part 2 video. I'm trying to break these up into smaller videos so that they're easier to upload on to YouTube.